Welcome to The Explainer. Today, we're sprinting straight into the deepest mechanics of computing. Look, if you really want to master modern technology, you've got to understand its foundations, right? So we're cutting out all the fluff. We're getting straight to the point and answering one fundamental question. What actually is a programming language at its absolute core?
Okay, let's dive right into this because it's a massive gap. Have you ever stopped to really think about how fundamentally incompatible human thoughts are with raw hardware? I mean, how does a cold, completely inanimate piece of silicon actually understand your complex commands? Bridging that gap? That is literally the foundation of our entire digital society.
Section 1. The core problem. Two very different thinkers.
To understand programming, we really have to start at absolute zero, the CPU. Let's bust the jargon right here. Your processor doesn't understand English, it doesn't know math notation, and it definitely doesn't understand logic. Its entire vocabulary is incredibly literal. It just takes a number from one tiny storage slot, adds it to another, or maybe flips a bit. That's it. That raw numeric instruction set is machine code. It's the only thing the hardware actually executes, and it is completely devoid of any abstract thought.
So we have this brutal contrast. As humans, we naturally think in concepts. Things like, hey, if the user's balance is greater than the price, go ahead and make the purchase. But machines, they process millions of raw, seemingly random numeric instructions that honestly look like complete gibberish to the human brain. A programming language is that necessary, formal bridge between the two. It systematically converts our conceptual thought into literal mechanical execution.
Let's look at Section 2, Syntax versus Semantics, and exactly why languages cannot be ambiguous.
Now, what's really interesting here is that human languages absolutely thrive on context and ambiguity. But a CPU, it cannot guess what you probably meant. Everything requires an exact split. Syntax is the grammar, the uncompromising strict rules for arranging symbols. If you forget a single closing bracket, the code won't even try to run. On the other hand, semantics is the meaning, what that grammatically valid code actually causes to happen. And the terrifying truth in computing is that catastrophic bugs almost always happen when the syntax is mathematically perfect, but the semantic meaning accidentally wipes out your entire production database.
Let's move to Section 3 and see how this builds into translating code to action, exploring our strategies for actually speaking to the CPU.
Since the CPU only speaks that raw machine code, we have to mechanically translate our source code, and you generally have two main ways to do this. Compilers read and translate your entire codebase ahead of time. This is huge because it allows for powerful static analysis. Take Rust, for example. It uses its compiler's borrow checker to catch fatal memory bugs way before the program ever runs, which gives you blazingly fast, perfectly safe binaries. On the flip side, we have interpreters, like Python, which read and execute code line by line on the fly. You get much faster iteration when you're developing, sure, but execution is inherently slower. Plus, critical mistakes might only show up as runtime errors when you're already deep into a live application.
But there's also this really clever middle ground. Many languages, like Java and JavaScript, don't purely compile or purely interpret. Instead, they compile down to a super compact intermediate form called bytecode. Then a virtual machine acts like a simulated CPU to run it. What makes this absolutely brilliant is just-in-time or JIT compilation. Basically, the engine watches for hot code paths, the stuff that runs constantly, and compiles them down to raw machine code on the fly. It gives you a massive speed boost exactly where you need it most.
So, how do we organize all of this? Section 4, Abstraction and Type Systems, the rules of engagement.
And this brilliantly illustrates how we categorize the entire landscape of programming languages. You really just have to ask one simple question. How far away from the bare metal machine does a language allow you to stand? With low-level assembly, you're literally shifting memory around manually. Absolutely nothing is hidden from you. With high-level languages like Python or JS, the hardware is almost entirely hidden behind nice abstractions. But Rust occupies this really unique position right in the middle. It gives you the granular, zero-cost control of a low-level language, but it still provides the safe, high-level ergonomics of an abstract language.
Then you have type systems, which dictate the rules of your data. Let's do a quick rapid fire here. Statically typed languages check your data types strictly at compile time, while dynamically typed ones check them on the fly at runtime. Strongly typed languages enforce rigorous rules about mixing data, whereas weakly typed languages might actually silently convert data behind your back, which can be incredibly dangerous. By combining static and strong typing, modern languages effectively shift massive categories of bugs entirely out of your production environments. They force you to resolve them as compile time checks instead.
Beyond types, we also have paradigms. Think of these as philosophies for structuring your thought process. Let's blast through them. Imperative relies on explicit sequential steps. Procedural wraps those steps into reusable function blocks. Object-oriented bundles your data and behavior into objects. Functional treats code like mathematical equations, strictly avoiding any mutable state. And declarative? That focuses purely on describing what you want, leaving the how completely up to the system under the hood. The real power today is that modern languages are often multi-paradigm, letting you mix and match these architectural styles exactly as you need them.
Which brings us to the climax of our explainer. Section 5. Why so many languages? The reason for the ecosystem.
We've seen the mechanics, the abstractions, the paradigms, which raises the ultimate question. If one method is best, why on earth do we have hundreds of active programming languages? Well, because no single language wins at everything. Speed, safety, and developer iteration are fundamental trade-offs. Look at the real world. If you want raw, blistering performance for a game engine, you're going to use C++. If you need incredibly fast developer iteration to prototype a startup idea quickly, Python shines. But if you're building highly sensitive security-critical systems like smart contracts, you use Rust for its impenetrable compile-time defenses. You have to optimize for your specific bottleneck.
So the crucial point is exactly what our source material notes. Every choice made along these axes is a deliberate trade-off. Picking a programming language isn't just a matter of taste, and it definitely isn't about following the latest trend. It's a deeply meaningful engineering decision. You're deliberately choosing the specific constraints, the safety nets, and the architectural advantages that best fit the exact problem you are trying to solve.
Which leaves us with one final, provocative question. What is the best balance point for your next problem? The next time you face a coding challenge, don't just blindly reach for your default tool. Look at your project through this new structured lens. Does it need maximum safety? Do you need uncompromised speed? Or maybe rapid iteration? Once you actually understand the deep mechanics of what a programming language is, you hold the power to engineer the absolute perfect solution. Thanks for joining me for this explainer.